Welcome to the video lecture of Electronic Devices KEC 301. The unit that will be discussed in this video is Unit 4 and the topic is bipolar junction transistor. In the previous video also we have discussed about the bipolar junction transistor construction and its different configurations. So different configuration that we have seen: common base, common emitter and common collector configuration. Out of these three bipolar junction transistor configuration, I have discussed one, that is common base configuration, in which the base terminal is common between the other two terminals, that are emitter and collector. So the working of that has been discussed, its characteristics that already been discussed. So now in the same continuation with the common base configuration, we will see some other parameter related to the common base configuration. Alpha, that is current amplification factor. For alpha is the ratio of output current IC to the input current IE. So this alpha is defined for the common base configuration, where the output current is the collector current IC and the input current is IE. So alpha DC we can define as IC upon IE is the ratio of DC output current to the DC input current. IC is alpha IE plus ICBO. This alpha IE is the IC that we have seen. IC is equal to ICO plus ICBO. So ICO is written here as alpha IE. Ideally, the value of alpha should be 1, but in reality the alpha is always less than 1 and its value lies between 0.9 to 0.998. If we talk about AC value of this alpha, then alpha AC can be calculated as delta IC upon delta IE, and this should be for constant value of VCB. So this alpha that is defined for common base configuration, we have its AC value and the DC value with respect to the DC current, and AC value for the small change in the output current and the input current for the constant value of output voltage. Biasing of this configuration, the proper biasing of common base configuration in active region can be determined quickly using the approximation IC is nearly equal to IE, where we have ignored the IB current due to its very small value and assuming moment that IB is nearly equal to 0 microampere. The result is the configuration of the figure, and this figure is shown for the PNP transistor. How we can identify that it is a PNP or NPN? For a PNP transistor, this arrow is pointing inwards from the emitter side. So if we ignore the IB current, means the base current is 0, so the terminal is shown here is open. If this is an open terminal, then there is no flow of current and IB is equal to 0 microampere. The arrow of the symbol defines the direction of conventional flow of current IE, that is nearly equal to IC. The DC supplies are then inserted with a polarity that will support the resulting current direction. For NPN transistor, the polarities that are shown. So all the polarities will be reversed for NPN transistor to keep emitter base junction forward bias and collector base junction reverse bias. So here in this diagram we can see IB current is 0, so this base terminal is open circuited. Now the current will be flowing in the way on the path that is shown in the figure. From IE it will go to IC and it will form this path from emitter to collector and then collector to emitter. So is this type of circuit that in which IB is 0. So this is showing the establishment of the proper biasing management for a common base PNP transistor in the active mode of operation. Transistor amplifying action. If we see the figure, for example, there is a PNP transistor has been taken with three terminals, emitter, base and collector. The input side voltage is 200 millivolts and towards the collector side we have a resistance of 5 kilo ohm and the output resistance that is seen from the output side is 100 kilo ohm and the input resistance seen from the input side is 20 ohm. Input current is I suffix I and the output current is I load current. So to analyze about the amplifying action of the transistor, let's consider this diagram. The DC biasing does not appear in the figure since our interest will be limited to the AC response. For the common base configuration, the AC input resistance determined by the characteristics of that common base amplifier that we have seen is quite small and typically varies from 10 ohm to 100 ohm. The output resistance as determined by the curves of the characteristics that are also quite high and the more horizontal the curve, the higher will be the resistance. And typically it varies from 50 kilo ohm to 1 mega ohm, that is 100 kilo ohm for transistor of as shown in the figure. The difference in resistance is due to forward bias junction at the input side is base to emitter junction and reverse bias junction at the output side, that is base to collector region. Using a common value of 20 ohm for input resistance, we find that the current is the ratio of V by R. So input current will be V input by R input. V input we have 200 millivolts and R input is 20 ohm. So we get an input current of 10 milliampere. If we assume for the moment that alpha AC, that is current amplification factor for common base configuration, is 1. 1 means we have IC is equal to IE. So IL will be equal to I input and that I input we have calculated as 10 milliampere. So V load will be I load into R. So I load 10 milliampere multiplied by 5 kilo ohm. So we get 50 volts. The voltage amplification is V output upon V input. V output is load voltage, V load, and the input voltage is V input. And V load we have found 50 volts to the ratio of 200 millivolts. So the voltage gain will be 250. Typical values of the voltage amplification for the common base configuration vary from 50 to 300. The current amplification IC upon IE is always less than 1 for the common base configuration. So this characteristics should be obvious since IC is equal to alpha IE and alpha is always less than 1. The basic amplifying action that is produced by transferring a current I from a low to a high resistance circuit. So the combination of the two terms, that is transfer plus resistor, results into the name of transistor. So transistor name is, that is from transfer plus resistor, and bipolar is due to the two type of polarities, two type of charge carrier that contribute to the conduction. So it contributes to the complete name, that is bipolar junction transistor. So bipolar has a meaning with the respect to two type of charge carrier, and transistor is with respect to the term transfer plus resistor. Now coming to the next configuration of bipolar junction transistor, that is common emitter configuration. Common base configuration we have seen, in which base is common on the same ground. Here we will be having emitter as common terminal between the other two terminals. Here if we are taking emitter as common terminal, then the remaining two terminals will be base and collector. So we need to place the bipolar junction transistor and the batteries in such a way that the emitter terminal is common between the other two terminals. So here if you see the first diagram, that is for NPN transistor, in that we have this base terminal, collector terminal and emitter terminal. So here emitter is to be made common. So one battery is connected between base and emitter, and another one is between collector and emitter. If you recall the previous diagram of common base configuration, then at the input side we were having emitter and base. A battery was connected between emitter and base, and emitter and base junction was the input side junction, and collector and base was the output side junction. So here we have emitter as common. So here we have one input side junction as emitter base junction, and as the output side we have collector emitter junction. So now the emitter is common between collector and base. So its representation with the symbol of bipolar junction transistor. This is bipolar junction transistor. Emitter is common. We have one terminal collector and base. The base current is inwards, collector current is inwards, and the emitter current is outwards. This direction of current is based upon the flow of the charge carriers. As emitter is of n type, so the electron will move towards the base, and so the current direction will be outwards. So coming to the next second diagram, that is representing the PNP common emitter configuration, in which the emitter is common. The circuit configuration will connections will same as NPN, with the difference in the battery polarity and the direction of current. Polarity of battery will be just reverse to that of NPN transistor, to make the emitter base junction forward bias and emitter collector junction reverse biased, because input side we should have a forward bias junction, and at the output side we need to have a reverse bias junction to keep the device into the active mode. So here you can see the P, that is emitter, is of p type and it is connected to the positive of battery, and base is of n type, that is connected to the negative of the battery. So this junction is forward biased. And if we see the output junction, collector, that is of p type, is connected to the negative of battery, and emitter, that is of p type, is connected to the positive of the battery. So in that way The input side junction, that is emitter base junction, is in active mode, is in forward biased for both the diagrams, and collector emitter junction is reverse biased for both. So the input junction is forward biased and the output is reverse biased for the operation of the device into the active mode of operation. Now coming to the characteristics of the silicon transistor in common emitter configuration. Collector, the figure A is showing the collector characteristics and figure B is showing the base characteristics of the common emitter configuration. The magnitude of base current IB is in microamperes compared to the milliamperes of the collector current IC. Consider also that the curve of IB are not as horizontal as those obtained for emitter current IE in common base configuration, indicating that the collector to emitter voltage will influence the magnitude of collector current. The active region for the common emitter configuration is the portion of the upper right quadrant that has the greatest linearity. That is, that region in which the curve for IB are nearly straight and equally spaced. So in the figure, this region exists to the right of the vertical dashed line at VCE saturation and above the curve for IB equal to 0. The region to the left of VCE saturation is called the saturation region. In the active region of a common emitter amplifier, the collector base junction is reverse biased while the base emitter junction is forward biased. You will recall that these were the same conditions that existed in the active region of the common base configuration. The active region of the common emitter configuration can be employed for voltage, current, or power amplifications. The cutoff region for the common emitter configuration is not as well defined as for the common base configuration. One point is to be noted down on that on the collector characteristics shown in the figure, that IC is not equal to 0 when IB is 0. For the common base configuration, when the input current IE was equal to 0, the collector current was equal only to the reverse saturation current ICO, so that the curve IE is equal to 0 and voltage axis were for all practical purposes that 1. So this was the characteristics, that is collector characteristics, that is plotted between VCE and IC, and base characteristics, that is on the x-axis we have VBE and we have the current IE. Next we have the figure, the conditions surrounding the newly defined the current that are demonstrated with the assigned reference directions. For linear, that is least distortion amplification purpose, cut off for the common emitter configuration will be defined by IC is equal to ICEO. ICEO means I, collector to emitter current with base open circuited. In other words, we can say that the region below IB is equal to 0 microampere is to be avoided if an undistorted output signal is required. When employed as a switch in the logic circuitry of a computer, a transistor will have 2 points of operations of interest, one in the cutoff and one in the saturation region. The cutoff condition should ideally be IC is equal to 0 milliampere for the chosen value of VCE voltage. Since ICEO is typically low in magnitude for silicon material, cutoff will exist for switching purpose when IB is equal to 0 microampere or IC is equal to ICEO for silicon transistors only. For germanium transistor, however, cutoff for switching purposes will be defined as those conditions that exist when IC is equal to ICBO, that is collector to base current with emitter open circuited. This condition can normally be obtained for germanium transistors by reverse biasing the base to emitter junction a few tenths of volts. Recall for the common base configuration that the input set of characteristics was approximated by a straight line equivalent that resulted in VBE is equal to 0.7 volts for any level of IE greater than 0 milliampere. For the common emitter configuration, the same approach can be taken, resulting in the approximate equivalent of the figure. The result supports that our earlier conclusion that for transistor is in on or active region. So active region, the base to emitter voltage is 0.7 volts. So common emitter amplifier currents can be defined as IE is equal to IC plus IB and IC is equal to alpha IE. Actual current IC is equal to alpha IE plus ICBO, where ICBO is the minority collector current. ICBO is usually so small that it can be ignored except in high power transistor and the high temperature environment. When IB is equal to 0 microampere, the transistor is in cut off, but there is some minority current flowing called ICEO. ICEO is defined as the ratio of ICBO divided by 1 minus alpha for IB 0 microampere. Current amplification factor for common base configuration we have defined as alpha. So we have the another term that is beta with that is related to the common emitter configuration, that is beta, and that is the ratio of output current to the input current. So here for this common emitter configuration, the output current is IC and the input current is IB. So beta is DC value will be defined as IC upon IB, and that is determined by a particular operating point on the characteristics. So beta DC, in the similar way we had for common base configuration, we had it for the common emitter configuration as beta, and in common emitter we had alpha.